All right, continuing on here in section 7. We're going to look at composition of the inverse functions with the regular trig functions. And they're going to be a little bit weird, so I have a lot of information here on the board. I'll kind of talk through it a little bit, and then we'll jump in and try a few examples. But some strange stuff is going to happen here. And it happens, again, because we had to do so much restricting with these functions and because of the output values that they actually have. So, for starters, if you have an x value that's between -1 and +1, then the sine of the sine inverse of x is x, and the cosine of the cosine inverse of x is also x. That works because, remember, the only things you can plug into those inverse sine and cosine functions are numbers between -1 and +1. So if x here is 7, this whole thing falls apart. It doesn't work. If x is just 0.1, you're fine. The sine of the sine inverse of 0.1 would just be 0.1. If x is a real number, because again, tangent can spit out any number you want, then you can put the tangent with the tangent inverse and get whatever number was on the inside. Now, what happens when we switch those around? So all of these have the regular trig function on the outside. Let's put the regular trig functions on the inside. And you can see we've got a whole bunch of different options here. For sine, if sine is on the inside and its inverse is on the outside, if that x on the inside is between -π/2 and +π/2, you get the same output. If not, well, we'll have to deal with that, and we will. We'll look at least one example where we're not in the right place and see what happens. If x is between 0 and pi, then the cosine inverse of cosine x just spits out x. And last but not least, if x is between -π/2 and +π/2, not including those endpoints, okay, that's different from sine, where we did get to include those endpoints, not including the -π/2 and +π/2, then the tangent inverse of tangent is just x. All right, so now we have a couple of fairly straightforward examples putting in a function and its inverse together. The first one, we have the sine of the sine inverse of 0.7. Well, 0.7 is between -1 and +1, and so this fits the criteria perfectly that was laid out on the last board. Because that's between -1 and +1, basically the sine and the inverse cancel each other out, and we get 0.7. We get the exact same thing as what went into it. Now this one's different. This one, you'll notice I wrote down undefined. Here's why. The cosine of the cosine inverse of 4 doesn't work. Just try it on your calculator. Type in cosine inverse of 4. Just do this one bit on the inside and see what you get. If you do that, your calculator is going to give you an error message. Because, again, the only things that can go into the inverse sine and cosine functions are values between -1 and +1. If you're not between -1 and +1, it won't work. It will be undefined. So you can't do that one. All right, don't worry. I've got more examples. Okay, here's my next example. This one's definitely more complicated. We have the tangent inverse of the tangent of 4π/3. And here's why this one's more complicated. 4π/3 is not in between -π/2 and +π/2. If you're looking at my graph, at a graph here with the angle put onto it, 4π/3 is over here in the third quadrant. Okay, I'll let you try and convince yourself of that, but that's where it is. And -π/2 to +π/2 is just the right-hand side of our what was our unit circle. So we need, if this were over here on the right-hand side, we'd be all set. It would just be that value that was in there, but it's not. So we're going to have to fiddle around with this just a little bit. So here's how it's basically going to work. The reference angle for 4π/3 is π/3. And that's really going to be the key here. Okay? So in this particular instance, tangent of 4π/3 is a positive value. If we think about the tangent of positive π/3, which would be right about here, somewhere in the first quadrant, if we think about tangent of positive π/3, that would also be a positive value. So tangent, basically what I'm trying to say is this, that the tangent of π/3 and the tangent of 4π/3 give us the exact same thing. Why is that important? Because π/3 is in between -π/2 and +π/2. And since these will give us the same value, the inverse tangent would then spit back out the same thing for both of them. And it's going to spit out positive pi over 3 because these are identical. Okay? Now, in this case, this worked because the tangent of 4 pi over 3 is positive, and so is the tangent of pi over 3. If the tangent of this number here had been negative, then it just would have been the same as negative pi over 3, and it still would have worked. It still would be the reference angle, but we'd have to flip it down and use the negative pi over 3, which is down in quadrant 4. Isn't that fun? I can tell you're all super excited. Anyway, so good luck. I've got one more example, and it's going to be great. Okay, here's our last example in this whole chapter. Find the exact value of the tangent of the sine inverse of 2/3. And I know what you're thinking. You're like, wait a second, tangent and sine inverse, those aren't the same kind of thing. Why are we trying to put them together? Because it's really fun. So here we go. All right. Here's how this is going to work. And I mean, you can see the whole thing here, but here's how this is working. Remember, an inverse trig function spits out what kind of thing? The answer is an angle. Right? Normally we put angles into trig functions and a number comes out. When we do it backwards, we put a number in and we get an angle back out. So whatever this thing is, it is going to be an angle, and I'm calling it theta. And the important thing here is that this angle is such that its sine is 2/3. Okay, so I know I have some more stuff written here, but let's go over to my triangle. So the sine of this angle is 2/3. I'm drawing a triangle, taking advantage of the fact that I know that this angle is such that its sine, the opposite over hypotenuse, is 2/3. So I can draw a triangle. We've really basically done this problem before. We just haven't seen it look like this. So in order to find the tangent of that angle, because remember, this whole thing is that angle, I need the opposite over adjacent, 2 and a. So I need to find a, and then I can put together my tangent. So I pull out the Pythagorean theorem. A squared plus 2 squared equals 3 squared. 2 squared is 4, 3 squared is 9. When you subtract the 4, you get a squared is equal to 5. And out pops that a is the square root of 5. I bring it back. We have 2 over the square root of 5. And so when we rationalize that denominator, multiply the top and the bottom by that square root of 5, we get 2 square roots of 5 over 5. And so what we're really doing here is we're taking advantage again of the fact that this inverse is just an angle such that sine of that is 2/3. And we're using that to draw the triangle. And so this is really actually a really kind of fun little problem. I really like it. And yeah, there we go.